Okay, so part 1A is just one of these standard questions which you can learn the answer to in advance, and those should then be the really easy marks that you make sure you get in the paper. So if you haven't learnt these things, these are the ones you're going to be really annoyed about when you don't get it. So why is a phenol more reactive than a benzene ring in reaction with an electrophile like bromine? There are just three things you have to make sure you get. The first then is to remember that it's all about the lone pair on the oxygen in phenol. Okay, so it's that lone pair on the oxygen that is the key thing, because that becomes delocalized into the ring. That's the first point. Lone pair on the oxygen, delocalized into the pi electron system. You've got to use the right word, delocalized, so not just spread into or anything like that, delocalized into the pi electron system. Second mark is for saying that that increases the electron density. Again, you've got to use the right term. It's electron density. It's definitely not electronegativity. People use that word all the time to mean things it doesn't mean. It's not the right word here. Increased electron density. And the third thing is that it therefore makes the ring more attractive to an electrophile. Again, attractive is the key word there. Okay, so straightforward 3 marks. B part 1, again, this is one of these standard things that you need to have pre-prepared, ready to explain. So how does gas chromatography work? The stationary phase is a liquid which lines the inside of the column. The mobile phase is a stream of gas flowing through the column. That's the level of detail you need. You don't need any complicated explanation of the equipment. So just stationary phase, liquid lining the column. Mobile phase is a stream of gas flowing through the column, and the point about the separation is that as substances flow through, they will tend to dissolve in the stationary phase, and the more soluble they are, the more time they'll spend dissolved, and therefore the longer it will take them to reach the other end. So all you say is that separation is based on substances dissolving in the stationary phase, and the more soluble they are, the longer it takes. Sometimes people just say vaguely, it depends on the solubility. And that may be enough, but it's a little bit vague. It's like saying, whether you end up in jail depends whether you murder people or not. And the trouble with that is that people are then left unsure whether they should be murdering people or not. And it's the same with this. It's not really enough to say it depends on solubility. You've got to say the more soluble it is, the longer it takes. Okay, so the next bit, B part 2, is a lot more challenging, because now you've got to use your understanding of chromatography and of the reaction chemistry to make sense of what's going on here. So this is Lewis compound, and the point is that it's a phenol, and what you're supposed to remember is that that OH group in a phenol activates the ring for electrophilic substitution. So straight away, you're expecting that there might well be a substitution reaction. And it's going to be at that position, because remember, phenol has an activated ring at positions 2, 4 and 6, but 4 and 6 are blocked by these carbon chains, so only position 2 can substitute. It also has an alkene group, which is here. And again, what you need to remember is that alkenes react by addition, not by substitution, but by addition. That's year 1 chemistry that you need to go back and learn if you'd forgotten that. And so we may be expecting the bromine to add across here. So if we take that idea on board, the 2 reactions we might expect to happen would be, first of all, the substitution reaction, which is going to go like this. So there's the starting compound, reacts with only 1 bromine because there is only 1 position that can react, and so we're going to get this. With the bromine there, and that one, because it's substitution, the hydrogen that comes out, remember, combines with the other bromine, and so we get HBr as the other product. So that's the first reaction, and if you add up the MR of that lot, you find that that comes to 212 is the MR for that one. So that's consistent with this peak in the gas chromatograph, where the phenol group has reacted, produced a compound with MR of 212, and therefore the molecular ion peak in the mass spec has an M over Z of 212. The other possible reaction is the addition reaction. So, same starting compound, but this time it's this group that's going to react. And all that happens, remember, with all alkene reactions is that the pi bond breaks and you just create two new sigma bonds, one at one end, one at the other end. So you'll just get one product because you're not substituting anything, and you're going to get one bromine there and one bromine there. Put on the detail, and that's your other product. And that one, of course, is going to have a bigger MR because it's got two bromines, not just one, and if you add it up, it comes to 292. You're having to be careful with these MRs because remember it's bromine 79 specifically, so when you're adding them up, you've got to make sure that you just use 79 rather than the normal relative atomic mass, which is 79.9, to get these numbers. So you're just using the individual isotopic mass of 79. So that's your 292 peak accounted for. And so on the basis of that, you say, right, these are the two possible compounds, and that's your answer for part 2. The next bit, it asks you on the basis of that to state which is more reactive, the phenol group or the alkene group. Now the point about Lewis' experiment was that you only added enough bromine to react with one of them, because there are equal moles of bromine in the compound, so you wouldn't expect it to be able to react with both, or at least it can't react with both in all of the molecules. So effectively you set up a competition, right, between the two reactions, and so what you look at are the sizes of the peaks in the gas chromatograph, because remember the size of the peaks tells you how much of the stuff you've got. So this one is clearly the biggest peak, the 212 peak, and that's the one you get when the phenol reacts. So what you say is that the phenol is the most reactive compound, and you know that because the product when the phenol groups react is the one that's formed in the greatest amount. You know, it's like if you and I are competing to pick up apples, if you pick up apples quicker than I do, you end up with more apples. Okay, so if these two groups are competing for the reaction with the bromine, the one that reacts faster will get more of the bromine. That's the basis of the experiment. So your conclusion is that the phenol group's more reactive because you get more of this product, which is the one you get when the phenol reacts. Part 5 is asking us to now say, well, if you wanted to make that more quantitative, quantitative means actually put numbers on how much more reactive it is. Well, you could do that by measuring the area underneath each peak. So remember the area, which means that the area is proportional to the amount of the substance in moles. And so by measuring the areas under the peaks, you could quantitatively say how much more of this there is than of that, and therefore how much faster the phenol reacted than the alkene group. Part 6 is asking us about these two little peaks at 11.6 and 14.4. And the starting point is that this one, we're given the M over Z for the molecular ion peak is 370, which means that comes from something which has an MR of 370. And just comparing it with these, you can see that it's just 78 more than that one, so that corresponds to one extra bromine going in and a hydrogen coming out. So you can see what's happened here, which is that instead of it doing either this or this, it's done both. So we get a small proportion of molecules because it's only a little peak, but in that small proportion both reactions have happened. And so the compound that corresponds to the 370 is basically one where we've had both substitution in the ring, so it's got the bromine there, and addition to the alkene group, so we have the two bromines there and there, and that gives us an MR of 370, and therefore it accounts for the molecular ion peak. So the key is always use these numbers up front, don't just kind of use them to check at the end that it might be right, just use them to help you figure out what looks like it's gone on here. So this one, it doesn't give us an MR for, but you can see, remember there was only enough bromine to react once with each molecule. So what that means is that if a few of the molecules have reacted twice, there will be some molecules left over which don't have any bromine left to react with at all. And so that suggests that what that is unreacted compound, whatever it is. In other words, it's this, which just didn't have any bromine left to react with. So this is the one that gives that peak, simply because we had a limited amount of bromine. If some of them have reacted twice, it leaves not enough bromine for some of them to react at all, and so that's what that one is.